In 2020, more than 14 billion miles from Earth, NASA's Voyager 1 spacecraft drifted into a region of space where nothing should have been strong enough to notice it at all. And yet, buried in a stream of data traveling back to Earth at the speed of light, taking over 20 hours just to arrive, mission scientists found something that shouldn't have been there. A wall of magnetic field, thicker and more powerful than anything predicted by any model of interstellar space, wrapped around a spacecraft that was never supposed to encounter resistance out here at all. Stick with me for the next few minutes, because the story of what Voyager 1 actually ran into in deep space is stranger and far more real than most of what you've probably seen about it online. To understand why this matters, you have to understand where Voyager 1 actually is. Launched on September 5th, 1977, on what was originally planned as a 4-year mission to fly past Jupiter and Saturn, Voyager 1 finished that primary mission back in November 1980 and just kept going. In August 2012, it crossed the heliopause, the invisible boundary where the sun's solar wind finally runs out of pressure and the true interstellar medium begins, becoming the first human-made object to leave the bubble our sun carves out around our solar system. Today, the spacecraft sits somewhere around 15.5 billion miles from Earth, moving outward at roughly 38,000 miles an hour, carrying a radio transmitter so faint it broadcasts with about the same power as a refrigerator light bulb. By November of this year, it will cross an entirely new milestone, becoming the first object ever built by humans to sit a full light day away from Earth, meaning a single round-trip command and response will take 48 hours. Every signal it sends back has to be caught by NASA's Deep Space Network, an array of giant radio dishes spread across California, Spain, and Australia. And even then, the signal is so weak that engineers sometimes have to combine multiple antennas just to pull a coherent readout out of the noise. Voyager 1's twin, Voyager 2, launched slightly earlier that same year but took a longer, slower route past Jupiter, Saturn, Uranus, and Neptune, and remains the only spacecraft in history to have visited all 4 outer planets, before it too eventually crossed into interstellar space 6 years behind its sibling. Both spacecraft are still remarkably transmitting usable science data nearly half a century after launch, using onboard computers with a combined memory smaller than what a modern smartphone uses just to load a single photo. Now here's where the actual anomaly comes in, and it's not aliens, but it is genuinely strange. Right after crossing the heliopause in 2012, Voyager 1 entered what NASA scientists nicknamed the Magnetic Highway, a transitional region where the sun's magnetic field lines connect directly with interstellar magnetic field lines, creating a kind of open channel that lets charged particles stream in both directions. Scientists expected the magnetic field strength to behave in a fairly predictable way as the spacecraft pushed further out. It didn't. Starting around 2020, at a distance of roughly 149 astronomical units from the Sun, instruments on Voyager 1 detected what researchers now call a pressure front, a sudden compression in the surrounding plasma that arrived without an obvious immediate trigger from solar activity. What followed was even stranger. The interstellar magnetic field strength around the spacecraft didn't just spike and settle back down the way earlier disturbances had. It climbed, and then it stayed elevated, forming what scientists have since labeled a magnetic hump, an extended region of unusually strong, tightly ordered magnetic field that persisted for roughly 2 years before the readings began to level off. For a region of space that was supposed to be close to empty, thin, and magnetically unremarkable, that kind of sustained structure was not something existing models of the outer Helios sheath had fully anticipated. If you're the kind of person who actually wants to understand what's happening out there instead of just seeing a scary headline, go ahead and hit subscribe, because the deeper story here is even better than the clickbait version. This wasn't actually the first time Voyager 1 had run into something unexpected out past the edge of the solar wind. Back in 2012, and again in 2013, mission scientists picked up what they nicknamed a tsunami wave, a shock wave triggered when the sun hurls out a coronal mass ejection, a massive cloud of magnetized plasma from its own surface. That wave travels outward for months, and when it finally slams into the thin, cold plasma of true interstellar space, it makes that plasma ring, almost like striking a bell, at a frequency the Voyager 1 team could actually detect and measure. Ed Stone, the mission's longtime project scientist at Caltech, described it exactly that way at the time, saying the tsunami causes the ionized gas out there to resonate, to essentially sing. Stone led the Voyager mission for nearly 50 years, from before either spacecraft launched in 1977 until his death in 2024, making him one of the only people in the history of space exploration to guide a single mission across virtually his entire scientific career, watching it go from a planetary flyby to humanity's only direct probe of true interstellar space. A third tsunami event, detected starting in February 2014, lasted so long that Voyager 1 traveled an additional 250 million miles, while the reverberations were still being picked up by its instruments. Then, in 2021, a research team led by Cornell astronomer Stella Koch-Ocker went back through years of Voyager 1's plasma wave data and found something nobody had specifically been looking for: a persistent, extremely faint hum, a continuous narrowband signal buried in the noise that had been quietly present since at least 2017, allowing scientists for the first time to measure fluctuations in interstellar plasma density on a near-continuous basis instead of only during rare, dramatic shockwave events. So when you put all of that together, the pressure front in 2020, the sustained magnetic hump that followed it, the tsunami, waves, and the persistent underlying hum in the plasma itself, you get a genuinely strange and only partially explained picture of what the space just outside our solar system actually behaves like. So when you put all of that together, the pressure front in 2020, the sustained magnetic hump that followed it, the tsunami waves, and the persistent underlying hum in the plasma itself, you get a genuinely strange and only partially explained picture of what the space just outside our solar system actually behaves like. A separate spacecraft, Voyager 2, which crossed the heliopause in a different direction in 2018, has recorded its own version of these events too. 2 pressure fronts and 1 shock of its own, giving scientists 2 independent vantage points on the same turbulent boundary region for the first time in history. Comparing the 2 spacecraft's data has turned out to be almost as valuable as either dataset on its own, because it lets researchers separate what's a genuinely local anomaly around one spacecraft from what's a broader galaxy-scale feature of the heliosphere's outer edge. This is where the internet version of this story tends to go off the rails. Viral posts and clickbait videos have taken these real anomalies and dressed them up, with claims of leaked NASA insiders, mysterious shielding zones, and hints of alien megastructures, none of which trace back to any actual mission scientist, peer-reviewed paper, or NASA statement. It's worth being direct about that, because stories built this way tend to spread faster than the real science ever could, precisely because they promise an answer instead of an open question. NASA has never issued any statement resembling those claims. No mission scientist associated with the Voyager program has been quoted making them, and the anonymous insider language that shows up across dozens of nearly identical posts online is a pattern typically associated with fabricated stories rather than genuine leaks, which almost never spread through unverified social media accounts first. The real explanation researchers are working through is almost more interesting precisely because it's grounded in something we can actually study, verify, and eventually publish for anyone to check for themselves. A team, using data through 2024 and 2025, has been modeling these pressure fronts and magnetic humps as evidence that the outer heliosheath, the boundary layer between our solar system's influence and true interstellar space, is far more dynamic and structured than earlier, simpler models assumed, shaped by repeated compressions driven by the sun's own 11-year activity cycle, colliding with a genuinely turbulent local interstellar medium. None of this is comfortable for the spacecraft itself either, because Voyager 1 is also fighting a much more mundane and much more certain kind of encounter, a slow, irreversible loss of power. Its plutonium-238 generators lose about 4 watts of energy every single year, and NASA has been shutting down instruments one at a time to keep the spacecraft transmitting for as long as physically possible. The low-energy charged particle instrument was powered down in 2026, following the cosmic ray subsystem the year before, leaving only a handful of instruments, including the magnetometer that detected the magnetic hump in the first place, still gathering data. None of this is comfortable for the spacecraft itself either, because Voyager 1 is also fighting a much more mundane and much more certain kind of encounter, a slow, irreversible loss of power. Its plutonium-238 generators lose about 4 watts of energy every single year, and NASA has been shutting down instruments one at a time to keep the spacecraft transmitting for as long as physically possible. The low-energy charged particle instrument was powered down in 2026, following the cosmic ray subsystem the year before, leaving only a handful of instruments, including the magnetometer that detected the magnetic hump in the first place, still gathering data. By most current estimates out of the Jet Propulsion Laboratory, Voyager 1 will likely stop transmitting entirely sometime in the early 2030s, not because it hits anything out there, but simply because it will finally run out of the power needed to keep even one instrument or its radio transmitter alive. It's worth pausing here to appreciate just how much engineering improvisation has kept this spacecraft alive this long in the first place. Back in late 2023, Voyager 1 suffered a serious communications anomaly, sending back what engineers described as a repeating, garbled pattern instead of usable science and telemetry data. For months, JPL engineers worked the problem essentially blind, unable to run normal diagnostics on hardware designed nearly half a century earlier, using documentation written by engineers who, in many cases, had long since retired. They eventually traced the fault to a single corrupted chip in the spacecraft's flight data subsystem memory. And rather than trying to repair something physically unreachable more than 15 billion miles away, they rewrote the affected code to route around the damaged section entirely, restoring all 4 of Voyager 1's active science instruments by the following spring. That kind of remote surgery on hardware older than most of the engineers performing it has happened more than once across the mission's history, and it's a big part of why so many scientists treat every new signal from Voyager 1 as something close to a small miracle, a machine that keeps finding new ways to survive, long after its designers assumed it would have gone silent. And that's really the encounter worth paying attention to. Not a fabricated alien structure, but a 49-year-old machine built with 1970s technology, still returning genuinely new physics about a region of space no other spacecraft has ever directly sampled. Every pressure front, every magnetic hump, every faint plasma hum Voyager 1 has picked up is real data that's actively reshaping scientific models of what the true boundary of our solar system looks like. Models that didn't exist before this one aging probe pushed further than anyone in 1977 ever expected it to survive. When it finally does go silent, whether that's in 2030, 2031, or a little later if engineers manage one more improbable workaround, Voyager 1 won't stop moving. It will keep drifting outward at 38,000 miles an hour, carrying the golden record, that gold-plated disk of Earth's sounds, images, and greetings in 55 languages, assembled by a team led by Carl Sagan, on a trajectory that will eventually bring it within a few light years of the star Gliese 445 in roughly 40,000 years. A silent ambassador for a civilization that, by then, will have long since moved on from whatever it was doing in 2026. There's something worth sitting with in that timeline. 40,000 years is longer than the entire span of recorded human history several times over, and Voyager 1 will still only be passing. Near one star, not arriving anywhere, not stopping, just continuing to drift through a galaxy that is, by any measure, almost entirely empty space. The odds of the golden record ever actually being found by anyone or anything are astronomically small, and the scientists who built it always knew that. It was never really designed as a message with realistic odds of delivery. It was designed as a statement, a record that humanity existed, reached this far, and tried to say something true about itself before letting the silence take over. The real story of Voyager 1's deep space encounter isn't that it found something that shouldn't exist. It's that we're still learning in real time just how strange and unfinished our understanding of the space right outside our own solar system actually is, and that a spacecraft older than most of the people watching this video is still the only tool humanity has ever had to study it directly. If you want to see what Voyager 1 sends back next, as it approaches that one light day milestone later this year, make sure you like this video and subscribe with notifications turned on. Because whatever this old spacecraft finds next, we'll be breaking it down as soon as the data comes in.